Hello everyone. So in this video, we are going to discuss about the unit one, first order differential equations. So in that, reducible to exact differential equations. So let me explain one by one. The first one is integrating factor, I of definition. If a differential equation of the form mdx plus ndy equals to 0, which is not exact, then it can be made exact by multiplication by a suitable factor. That is, a function of x and y becomes to exact. The factor is called integrating factor. The second one, the homogeneous differential equations. Homogeneous differential equation definition, which the differential equation of each term has satisfying this same degree. For example, xy minus 2y square dx minus x square minus 3xy dy. So in that xy 1 plus 1, 2. Y square is degree is 2 and x square degree is 2. X, y, 1 plus 1, 2. So each and every term in this mdx plus ndy form, weighing or satisfying that each term is degree 2, then the differential equation is called homogeneous. Next, we'll move to the third one, non-homogeneous differential equations. When a differential equation is not a homogeneous, then we can say that non-homogeneous differential equation. So here we are the example, you can observe the 2 plus 1, 3, but the second term 2. In the second, x square is 2 and x by 2, 1 plus 2 is 3. So here one term contains a 3, other term contains a 2. So this is not a matching of the homogeneous differential equations. So that's why each term does not have the same degree. Therefore, the differential equation is a non-homogeneous. Next, fourth one, reducible to exact integrating factor. A differential equation of the form mdx plus ndy equals to 0 is not exact, then obviously we need to convert into exact by multiplying a suitable factor, a function of x and y. B becomes to the factor is called the integrating factor. So this integrating factor plays the vital role when we are getting into the general solution. So actually, this is the first method. We need to convert, if the given differential equation is not exact, we need to convert into the exact differential equation. So the first method is integrating factors, which is a very, very easy to get with the limited period of problems. And but whereas a homogeneous, non-homogeneous, these are all according to the depends on the problem. We have to get the general solutions, but integrating factor will be a limited problems only. It can be applicable. Now we can see that exact what are the methods we are going to reducible into exact differential equations when the problem model or the problem is not in a exact problem, then we have to convert. So here I mentioned 1, 2, 3, 4, 5. The first one is integrating factor. That's what we discussed now, also known as a grouping method. Second one, just now we discussed what homogeneous, and then next non-homogeneous also. And the fourth and fifth are not specifically mentioned that this method is homogeneous, this method is integrating factor, like that. And also we can see that in the method 2, again specifically they mentioned that mx plus ny is not equals to 0, but here we are taking if equals to 1 by mx plus ny. In the third method, y into some function plus x into some function dy equals to 0. But here, mx minus ny not equals to 0. But here we are taking that I of 1 by mx minus ny. Fourth method, n is a small. That means if nth term, the second term will be there. So that second term is small, then we are taking 1 by n into dou m by dou y minus dou n by dou x equals to f of x. And here if equals to e power integral f of x dx. This is especially function which x alone only. And the method for m dx plus n dy equals to 0, here m is small. Then 1 by m into dou m by dou x minus dou m by dou y equals to g of y. Here the if equals to e power g of y into dy. Here the function is y alone. Then, so these are all the methods, condition, type of equations, and if. Just now we discussed all the things. Equations reducible to exact differential equations, and also known as standard rules for finding if. And you can observe that in every method, if plays vital role to get the general solution. And the method one, again, integrating factor founded by the inspection method or grouping method. Here we had to observe that all the 12 grouping method formulas are getting by inspection method. You know very well x into dy plus y into dx equals to d into, this is looking like a multiplication method. Here, this is looking like a addition, but here something is missing because this x we can't differentiate that. If you differentiate that the function, we need to get that. No? So differentiation and integration are inversely proportional, right? So if you use it, that we can't get, but we need to get into that the both will be the equal. So that's why we had to write, which is by inspection method, d into x square plus y square by 2. Y dx minus x dy by y square. So this we can write like u by v method. So x by y. This is also u by v method. Here the missing is negative. And this is one more formula looking like a tan inverse of y by x. And this is looking like a log x y. And this is looking log x square plus y square divided by 2. And looking like u by v. Looking like u by v. Looking like u by v. And this is, and we can observe that here the method one example, how we are going to solve that the inspection method, x dy minus y dx is equals to xy into y square dx. Here you can observe that x dy minus y dx, so which is looking like, because negative will be there according to the formula, this is y by x. Or x by y will get that. So here observe that in the RHS, y square is there. So if y square will be there, and we can guess that here this is x by y form, right? So that's why we are writing x by y, x by y. But here dy is there, but we had to change, putting into the negative and writing the formula of d x by y equals to, and integration of this x dx equals to x square by 2 plus c. And this is the